Okay, good morning. Last week we talked about diffusion maps, at least those who had time. It's nice to see that we are a bit more now today again. About the diffusion maps, in the end we got a bit into, it got a bit fast. So I was wondering, but on the other hand, many of you weren't. Let's start with something new and add what I wanted to add to the stuff from last time, add it later or tomorrow or next week, because half of you haven't been here anyway. So what I wanted to talk about today is, you remember over the last times we had looked at pseudotime in order to bring our cells into an order, and when we checked how specific genes change along with pseudotime. And we actually see a lot of variance along this change, and we have to ask how much of this has biological meaning and how much is of technical origin. And I want to first talk about this, and then I want to get today up to the question of how can we actually improve on the denoising of getting rid of Poisson noise. And the fundamental idea here is to borrow information from the neighbors. So in a way, biologists are often dismayed that you have so low counts per cell in 10x sequencing. But one shouldn't forget that on the other hand, we have very many cells. And an important rule to keep in mind is that in biology, we are never interested in a single cell, even though we talk about single cell sequencing. Because after all, in science, we don't talk about anecdotes. Whatever we see, we want to see in several samples. And even if we look at just one sample, we want to see things which happen to several cells. Because if some cell does something strange and you never see this cell again, it's not noteworthy. So what we are really interested in is properties which we find over several cells. Hence, having many cells which are similar is as valuable, is probably more valuable than having one cell deeply sequenced, because we can average over these cells. But we have to do this averaging in a clever way, because if we just put cells which are roughly similar together and average, when we might average out some noise, but also a lot of biological signal, because we made some rather arbitrary choice of which cells are similar enough to average over. And also you can gain a lot by doing the averaging in a mathematical, rather clever way. And that's what I want to talk about today. So what we have here now is, let's see, let's start with this. Unfortunately, this time I don't have as nice an R notebook, but I have here this R script where you can look through, and we will, maybe I should upload it in case you want to look at it while we're doing this. I quickly do this perhaps. We are here now. How do I do this? 3D/mint. Right. Under SCO Lecture, CP smoothing 2.R. Point. So if you now want to look at it, you can go to our usual lecture size, and then you just have to add smoothing2.r. I will later add it here to the bottom, but this is just a file which I have up here at the moment. You see here, this one, smoothing2.r, I've just added. But you can also just read here on the screen, so you don't need to look at that now and later. I put it in anyway. So what I use again is our EF Nagrico dataset. You remember that was this dataset from this EMBO journal paper, that one here. And who was on it? EMBO. Let's see if this thing is. The problem is that I can never type Daniel's last name correctly. So here we have it. No, not this one here. So that was the thing we looked at last time, which was about this effect of interferon to maintain stem cells. And we're not interested today in the interferon. All we're interested is in just having single cell data of adult neural stem cells, which differentiate by first getting activated, and then they go through the stages of transit amplification, where we run a couple of cell cycles to make copies, and then they become neuroblasts and final neurons. And that gives us a nice trajectory where we can look along. And what we will look at also today is not only what happens along this trajectory, but also what variability we have orthogonal to it. So how do two cells which have been assigned the same pseudotime, are they the same or do they differ from each other? Because the biology is probably not as one-dimensional as the trajectory tells us. So I have loaded here the data as usual. I just start this thing from scratch without reloading the data. So I load all my packages. I have here my usual data files with information on the cells and on the genes and the count matrix. And if this all doesn't fit together, then I'd better do restart it. Because session restart R. And let me get through the beginning. Now I have a moment to collect my widths while it loads the data, because that always takes half a minute. The first method to look at our cells is to use the local regression, that you might remember from last time. We used this GLM model where we always, in order to get the expression at a certain pseudo time point, we put a kernel over this pseudo time point, assign weights to all the cells at around this pseudo time, and then we try to fit a regression line which follows these weights, but not using a least square fitting criterion, but instead a maximum likelihood fitting criterion, where we want to maximize the likelihood that a Poisson distribution using the rate parameter given by the curve produces the counts that we observe. And that's what we start with, and then we try to expand around that today. So here again, we have call names, so I do my usual normalization. Remember that we do our normalization by dividing by the totals, when adding this one pseudo time. So here this is log 1p, means logarithm of this plus 1. And my PCA also takes a second. Should have saved this before, sorry, but I wasn't too too clever yesterday. Come on. Why is the PCA so slow? Last time it was really fast. I remember what I did last time to make it fast. I've learned that the irlbar has a argument called work, where you tell it how much memory it should use. And this thing we can put really high to tell it we have enough memory. We don't need sorry that everything is a bit slow today. It seems that that our Papagai computer is also a bit overloaded. Yeah, as you can see, somebody is running a lot of BAM compare stuff. So if we have to wait a bit, let's blame it on Martina. And now this is a problem. Why does it take so long? Come on. Usually this is done in 10 seconds. Yes. Yeah. Yes, I mean, the one thing that we did, exactly, you might remember a couple of weeks ago, we made this little calculation where we asked if we have counts from different cells for the same gene, and we assume that the biological signal, so the sort of rate parameter that's into the Poisson follows a log normal distribution, that the when we can combine this with a Poisson in order to see the overall variance. And what we found back then is, let's try to write this down again. Something is really wrong with this computer today. We said that Qi, let's say, is the expression strength of a gene in cell I, and we say this follows some distribution with variance with mean mu and standard deviation, let's call it gamma mu. So gamma is my coefficient of variation, so the standard deviation relative to the mean. And when I say that Ki, the count that I actually observe, follows a Poisson distribution, Ki given that Qi follows a Poisson distribution, where we say the rate parameter is given by this Qi times some factor Si, which we said is something like the cell size, how many counts we get in total for the cell. And one that we put in the end is that we then ask, what is this of course implies that the variance of Ki is the same as the mean, SiQi, and what we then ask is, what is the variance of Ki if I integrate out the dependence on Qi? And we used this law of total variance, and we came to the conclusion that this actually decomposes in the variance which we get due to the Poisson noise, Si mu, so mu from the gene, plus Si squared gamma squared mu squared. Or if I take the coefficient of variation, so var Ki divided by mu I get the coefficient of variation I have to divide by the square. I get Si over mu plus Si squared gamma squared. So as usual, our Poisson part is that part which goes down with the expected read count. Right? The higher Si is, the Si should be here at the bottom. Var Ki, right. This is why it's wrong, because I have to divide, want to divide Ki by the expectation of, right, properly. Want to divide Ki by the expectation of Ki squared. And now let's write this correctly. The variance of Ki is this stuff, and the expectation of Ki is, of course, simply Si mu I, and so I can divide this, and then I have 1 over Si mu I plus, because I square this, somebody now help me, plus gamma squared. Yes, this is what I want. It's correct now, so that you can see this is the Poisson part, and this is the biology. And we see our biology, and these two, they just add up Pythagoreically. So we see that the biological coefficient of variation gamma here gets into sort of a power struggle with this Poisson thing, and you can just see what's larger. If this part dominates over that part, then you can't see the biological variation anymore, which on the other way around tells you that in order to see a biological variation of, say, the gamma is 10%, you can just see from this how many counts you want to see in order to be able to see that. And obviously, if we then average over many cells, we can add up the counts which go in here. Because this part here, this can, of course, in practice, I approximate that part by just saying, okay, this is the expectation of a count, so let's take my actual count value to get a feeling about how big this thing is. And
so in experiments, would you first do this configuration or just run the experiment and later?
It depends a bit, because this depends on gene for gene. Typically, people will go, because for every gene you have a different value. So people typically go by experience. If you've done enough of them and you know what the typical count rate for genes are, then you have some feeling about how much you will see if you do things like that. If you have a certain... I should have got me a coffee. Then it would make more sense. Okay, now I finished my standard analysis. You see, I calculated the nearest neighbors here, and I calculated my UMAP. Let's quickly check that the UMAP looks as we expected. And this will be a slow lecture today if this thing doesn't get any faster. Okay. Here you see my UMAP. And again, just to orient us, this here are the quiescent stem cells, these are the active stem cells, here are the transient amplifying cells, and here are the neuroblasts. So our pseudotime goes from here to here. And the gene that we always used as an example and that I stick to as an example is aquaporin 4, that is an astrocyte marker, which is high in astrocytes and quiescent stem cells, and then goes down during our pseudotime. So I make myself here this table here, which contains for all the cells in the lineage. So for today, I will only look at the cells here within this block, and I get rid of all the others. And as you can see here, the cells in this block are 14,000 of the total 18,000. And here you see the gene counts for this gene aquaporin 4. Here you see which cell type is, and here you see the pseudotime that was assigned. And if we have a quick look at that, I should show you the pseudotime again, but you might remember from, where am I? Here. Here I now plot the counts against the pseudotime. So this is the pseudotime, this is the expression of aquaporin 4. Actually, what I really would like to show you before I do this is plus geom point aesthetics x is 9. C-bind as table UMAP. And what was the other thing when we need our table of all the data? I'll get to it. Why is this computer so slow today? This makes it really hard to work because one always feels so okay, next time I use a dedicated computer instead of that one that other people use as well. So what I wanted to show you here is that we first have a look at the pseudotime ggplot table null plus geom point aesthetics x is v1, y is v2, col is d is pseudotime. C-bind S table comma. Where's my plot? Here we have it. Okay. Size is comma 1. So here you see how the pseudo time goes from the left to the right. Plus cohort equal plus scale color viridis C. And the other thing that we should look at is the expression of aquamarine 4. And the way how I now do it, I will make you plot where we put on the y-axis the expression strength of aquamarine 4, and on the x-axis I put just the pseudo time where it runs here, as you can see, from 0 to 1. This is what we see here. And as you can see on the y-axis, I've just divided count over total and made my axis logarithmically so that you can read it off here. So this is essentially our expressed data. And here I've added 10 to the minus 5, because if I don't do that, then all the zeros will completely vanish, and now they turn up here at 10 to the minus 5. One thing I've done in my table here is that I added a column jitter, and this jitter just contains a lot of small values. And what I now do here in this plot is, instead of for the y-axis, I either plot count over total, or in case that it's 0, I use this jitter here so that you now can see better where there's many points and where there's only few points. The next thing I do is that I run the logfit package that we talked about 2 weeks ago. So we run this thing here, and you see in our logfit, what we've now done is we say we want to regress the count value onto the pseudo-time value, always making the kernel so wide that it covers 20% of the data points. We want to use a Poisson regression so that it maximizes not the least square, doesn't minimize square as in the least square criterion, but instead maximizes Poisson likelihood. And of course, in this Poisson likelihood, we have to put in the totals, because we want to multiply each read with a total. And the log goes in front because there's a log link, meaning the curve, it will predict a curve, add this total, then exponentiate it, and then compare this with the Poisson likelihood. That's what we did last time, and it still looks the same as last time. Here is the curve. And as you can see, the curve starts here, goes down, and now it even goes below my 10 to the minus 5, because I have so many zeros here that it pulls it down here. And that's what we seen last time. We can actually make reasonable inference about expectation values which are below our pseudo-time values. What I can also do is now judge about whether this is a good fit or not. And what I do, I ask logfit to predict for every pseudo-time value, for every cell, the curve position at this pseudo-time value. It now takes a bit longer, because first I calculated it for 1,000 equally sized points here. Now I calculate it for all the 14,000 actual pseudo-time points I get here. I should be finished any second now. Again, it takes much longer than yesterday. So you remember the logic. We said, and what I can do with this now is I calculate something which is called the Poisson deviance and the Poisson deviance residual. So let's first maybe quickly do this together. Here is my table, to which I have added here now here I have the pseudo-time, the counts, the total, and here I have a predicted expression. So predicted expression is the value of the purple curve at this pseudo-time. And what I can now do is I ask, what is the Poisson likelihood of actually, so Desproges, calculates a Poisson likelihood, the likelihood to actually observe this count value, 6 counts, if your expected expression is what it says here, predicted expression, this purple curve, times the total that we of course have. And we calculate this for every cell, and we want to get not the actual likelihood, but the logarithm of the likelihood, so that it says here log, which is why I have log is true. That's what I put here. So you see here, I calculate this likelihood, and let's first calculate it as why doesn't it do what I want? So I say here LL for log likelihood, and then put this thing that I've just calculated here, and now you get this log likelihood here. So here is the likelihood of getting these many counts if the Poisson expectation is what it says here times the total. And what you will typically do if you have something like this, you have a fit where you have your Poisson probability distribution or probability mass function given for some count k, and its likelihood L here. So this is the log likelihood to get k counts if you expect lambda counts. And if you use this in terms of a fitting, you want to know what is the maximum likelihood I could actually get if a fit were perfect. And obviously, the maximum likelihood you can get is if you use your actually observed count as the expected rate parameter. So if I say something like D poise 10,10, then it says, what's the probability of getting 10 counts if you expect 10 counts? And this probability is, of course, not 100% because there's still noise. This is why what one likes to do is subtract these and take the difference between these two values to see how far the fitted value is from the so-called saturated model, where every observation just gets the value it wants. And we call this quantity the deviance. And this likelihood is, of course, lower than that likelihood. So I have my signs the wrong way around. I want it this way. And I put in a 2 here. Why the 2? Imagine instead of a Poisson, I had here the normal distribution. Then, so if we have here F normal, given some count y, given a mu, then this would be 1 over 2 pi sigma square root e to the minus y minus mu squared over 2 sigma squared. So if you look at the log likelihood of this thing, then your log likelihood is, of course, y minus mu squared over 2 sigma squared. And this 2 here, we want to get rid of by multiplying with the 2 here. So that if we use this likelihood formula, which is general for all things, we get, in case of a normal distribution, we simply get z squared. So y minus mu over sigma and this thing squared. So this is just historical convention to do it like that. But of course, it has the advantage that if we actually use these things, then we notice that if we use it for a normal distribution, this so-called deviance is something which corresponds to the variance in the normal distribution. That's why it's called deviance. It's actually something like a z-score squared. It's the derivation from y from minus mu over sigma, and this is squared. So for normal, the deviance is something like z squared, where z, the so-called z-score in statistics, is always the observed value minus the expected mean divided by sigma. So this thing, which is a standardized normal, we call a z-score, and if we square it, then we get something which we call the deviance, and we want something else. We want to have the same for Poisson, so we fudge the coefficients by putting these d such that in the limit of big observation, you remember the Poisson becomes a normal distribution in the limit of big lambda, and so that this d here, the deviance, in the limit of big lambda becomes z squared. And this means we can make inference, and if you want to know whether this deviance is significantly far away from 0, people typically make a chi-square test because you know chi-square is the distribution of these z squares, and that works quite reasonably well. The other thing that we can do is that we get something which is corresponding to this z here by going from this to something which I call d, and I call this the deviance residual. You know, in a residual is the amount how far away you're from a fit. So we y minus mu, that would be a residual, and we can standardize a residual by dividing it by the sigma, so that we can get an immediate feeling how far we're out. So that we say if this standardized residual is more than 3, then by your usual rule, you know, one standard deviation out has 30% probability, 2 out has 5%, 3 out has 1%. So if you see a Z value, you can immediately say, is this still a normal noise or is this very far out? Like if you see more than, if you would expect that most Z values are below 1, a third of them are between 1 and 2, a 20th of them are between 2 and 3, and so on, because this is your usual quantiles in the normal distribution. And we want the same here, so that we can make roughly the same logic. So we change this d into a z value by saying d is the square root of this deviance times the sine of y minus mu. And that's what I've done here. So I've calculated here. Yeah. Or to see the goodness of fit. I'll plot it and then we can discuss it. So here, I've now taken this thing here. And so you see here, I have my likelihood. I subtract from the, what have I, that looked nicer before. Yeah, now it's fine again. So here you see I have calculated my deviance by calculating the likelihood of my counts given the fit that subtract the saturated model and taking it times 2. And then I calculated the deviance residual by taking the square root and adding a plus or minus sign depending on whether we are below or above. And now I will plot this. And here we now see the plot of this thing. And as you can see here, each point is now colored by its deviance residual, where green means we are above it and red means we are below it. And everything which is still sort of grayish is okay, and if it's saturated when we have more than 2 differences, so this is something which we should see only in 1% or so of all the stuff. Now this thing is really driving me mad today, because as you can see, it doesn't. What is it doing? It doesn't fit this properly. Okay, can't be helped. Okay, so what we can now see here is that the fitted curve, of course, those points which lie on top of the fitted curve, they have a residual around 0. They are now in gray, and we sit out. Does this now mean that our fit is bad? Of course, not necessarily, because we have assumed that the green and the red, we have assumed that all the noise we have here is only Poisson distributed. So that all the cells with the same pseudotime have, in fact, the same actual value Q, and that they vary around this actual value only due to a Poisson distribution. And this claim we can clearly refute. We see that there's way too many cells with a set value above it to say that there's really only Poisson distribution. So this is now precisely what Andreas asked. How can we see that here there is still actual biological variance? We can see it from the fact that the distribution of deviance residuals has a standard deviation much larger than 1, because if it were merely Poisson, then the distribution of deviance residuals should be roughly standard normal, and even though the shape might be a bit skewed, it should have a standard deviation around 1. We can have a look here at these deviance residuals to see how wide the standard deviation is, and you see there is here a big blob of those which nicely sit within the expected, and here is a socket of stuff which isn't. Probably, I would imagine that the white stuff here is the that the white things are the deviance residuals from up here, and the low things are the deviance residuals from down here. Maybe to verify this, I take.
It's just a little bit because based on the plot, you would expect the right part a little bit to the right, like not the other part.
Yeah. Here.
Like right, but it's because the actual counts are 0, right?
Yes. This plot is confusing. I should have put this bar down where we can make it. Yeah, this bar here is the 0 bar, so I should have put it at the very bottom, but of course I had to simply manually place it somewhere that you can see it. But this is why this here is gray, which tells us that the few counts which we occasionally say are so low that they are completely that the zeros that the expected expression is so low that seeing 0 count is fully within the expectation. While these things here, they are clearly way above the expectation. So what I now wanted to try is that I take here the predicted counts. So total times treble dollar fitted predicted expectation and treble dollar dev res. So here we had this plot here where we saw that there seems to be two populations, the narrow spike and this big socket. And if I now plot it that way, then we can in fact see that doesn't actually look as I expected. We can see that here, this big spike here, so which is the socket to the right here, these are probably those here, which are clearly way above. So here we can already conclude that in this area there seems to be two populations of cells. Those which really give 0 and those which give something, and it would be more appropriate to not say everything in this pseudo-time are one thing, but it rather looks like this is a bimodal distribution, with some of them having so low expression that we can't expect any counts, that the count should be effectively 0, and another subpopulation having appreciable expression, so that we see some counts. And we should keep this in mind, because at the end of either today's lecture or next week, we will actually see this when we use an alternative technique to smooth our data. So, what was here my next thing here? Now, one thing you might argue that, as I just said, this fit here, the deviance residual, shows us the expectation of the z values if we expect that all the deviation from the curve is only due to Poisson noise. But what if we assume, if we are more modest and say we know that there's some biological variation around this? What if we assume that the biological variation on our fit is something like 10% of the fitted value, and on top of that comes the Poisson variation? So far I have, in my current fit, I assume that the variance that I compare my deviance to, so I calculate it via deviance, but conceptually I could calculate it also by saying I calculate the difference between the counts, the observed count and the expected counts, and divide this difference. So the difference k minus the expected counts, which is, y hat times s. And I divide this by the expected standard deviation. And the expected standard deviation is at the moment given by this part here. But what if I say I want to add this part here to it? So I might say here, instead of dividing it by y hat s square root, I'd add some gamma, and let's say this gamma is 10%. And I do this. And now the gray area becomes much wider up here, while here at the bottom part, not much changes. Now, how have I done this calculation? Because there's, as I've just sort of hinted at, and now I realize that I maybe should have prepared this, there's two ways in all this GLM stuff. There is a whole zoo of different suggestions how you calculate with residuals. One thing with deviance residuals is the idea that I've outlined here, that we take the deviance and take the square. Another way, which if I'm not mistaken is called Pearson residuals, but I'm not so sure, is that you take your observed value, the counts k, and the deviation from this and divide this by the expected standard deviation. I shouldn't write whether it's ones for Pearson. I know that there's something called Pearson residuals, but I've forgotten whether this is what they call Pearson residuals. Actually, that's what compared we observed with a sign positive. Yep, probably sounds like it. Okay, but I've done it something else. What I have done, I stick to deviance residuals. And the way I calculated my deviance residual is that I replaced the Poisson distribution by a negative binomial distribution. Who knows what the negative binomial distribution is? So, the negative binomial distribution comes out of this issue here, that we have here, that we said here, I remember up here I said Q follows some distribution. Now what I would like to do is that I say Qi follows a log normal distribution. And when I say Ki given Qi follows a Poisson distribution, so for the moment, I ignore the size factors to make our life easier. So now size factors is 1. So I can just say this is the Poisson distribution around Qi. And now the question is, what is the distribution of Ki? And for this, I have to integrate out this dependence on Q. And if I do this, then of course I get that this follows some distribution F with f of k is integral over dq f plus of q times f log normal of q given some mu and sigma. And yes, because there's mathematicians in the room, let's put my differential at the end. Because no, that's a physicist's thing. In physics, we often have these multiple integrals where we say we have an integral over x, y, and z. In physics, we write then dx, dy, dz, and then f of x, y, z. Because when we can put the integral boundaries right next to the differential, you immediately see which boundary goes to this thing. Mathematicians don't like that because they say you can't be sure that the function f, that you can really swap around the integrals. You can only do this if certain preconditions are, I think it's called the theorem of some guy, Italian guy with V. And in physics, the preconditions of this thing are always fulfilled, so nobody ever cares. So this is what we do, and we have to solve this integral. Turns out this integral doesn't have a closed form solution if we put the log normal here. However, if I decide to be flexible, use instead of a log normal, I use a gamma with some mu and sigma, then I get a closed form solution out. Now I haven't prepared this, and actually it's a small lengthy, but let's just show it to you. I'm sure a negative binomial that the Wikipedia will tell us this thing. Properties, where is it? Gamma. Gamma Poisson mixture. Here, you see, if you have a Poisson distribution and the gamma distribution, and you have, right here, I should make clear that my integral runs from 0 to infinity, because of course the right parameter of a Poisson cannot be negative. So this is what we have. We take a Poisson with lambda, and we take a gamma distribution with some parameters which somehow parameterize mean and standard deviation over something. And when you put in the different things, and when you integrate the whole thing out, and magically you're left with this thing here. Which is a bit a strange magic that this happens, but yeah, believe me, I am now not, you see here a lot of stuff cancelled out between the two, and then you're left with this thing, which actually turns out to be some well-defined integral that you can look up, and that somehow involves this gamma function, which of course turns up if you use the gamma distribution. And then you're left with this thing, which looks strangely similar to the binomial distribution. You have a binomial coefficient in front, even though the binomial coefficient is here written with gamma function instead of a factorial. You have this thing, 1 minus p to the k, and then in the binomial it would say times p to the k, p to the r minus k. It's a bit different, but it resolves a little bit. This is why we call this the negative binomial distribution, because it looks like a binomial distribution, but has some minus signs where the binomial distribution has plus signs. But apart from the fact that the formula looks somewhat similar, it has nothing to do with a binomial distribution at all. It's simply what arises if you mix a Poisson and a gamma distribution in that manner. It also arises if you ask waiting time questions, something like, given a Bernoulli trial, as a successive Bernoulli trial, you know, the usual question is, what's the probability to have k successes within n trials? And that's the binomial distribution. What you can also ask is, what is the expected number of trials you have made until you have got k successes? And this question is answered also by the negative binomial distribution, which is why it's sometimes called the waiting time distribution. And this is why the parametrization of a negative binomial is rather weird. It has something called the size and the two parameters called the size and the shape. R is the number of successes you wait for, P is the success probability. Funnily, it turns out that you can reparameterize this into a mean, because obviously the mean is given by this, and into a coefficient of variance. So basically this gamma here, which turns out to be 1 over R, so the size. Every time I need to reparameterize from this thing to the mean and standard deviation, I get a headache. So I won't try to do this now, and you're welcome to try it yourself. But this is basically what I've done here. If you look closely, here was our original Poisson distribution, where I took the counts and I said, this is my expected mean. And now here I said, this is the counts, this is my expected mean as before. And then I added this size here, 1 over 0.1. And that means that gamma squared is 0.1. Actually, if I think about it, I wanted gamma to be 0.1, so gamma squared is 0.01. So in a negative binomial, this parameter size, which is called size in the Wikipedia, and also in R it's called size, in Wikipedia it's called R, is 1 over gamma squared. And I always keep forgetting this square. So now the one question you might ask is, what actually happens if I change this in a square? Does it look very different? Probably it gets a bit, all I've done is, I don't want to figure this one out. So one question you might now ask is it really okay to replace a log normal by a gamma? Now there's two ways to answer this. One answer, the statistician's answer is, who cares? My answer would be, because statisticians always say, if a function has roughly the right support and the right number of modes, it's probably good enough. If we come it from a more physical modeling perspective, you remember my argument for the log normal was always the mass action law.
And we can now say, okay, we consider the gamma as an approximation to the log normal, and we ask, is it sufficiently similar? And you can draw a couple of pictures and we'll find that the gamma distribution and log normal distribution do look quite similar as long as this gamma isn't too large. So if you have a gamma distribution with, let's look at a few pictures of gamma distributions. Gamma distribution. You see here for large sizes like this black one, this purple one, this green one, you can easily imagine you have this typical right skew, which is also typical for a log normal distribution. So if you were to take the logarithm of this here, you would get something which looks reasonably normal, at least if you stick to gamma distributions where this shape parameter theta is smaller than 1, so that it has the mode not sticking here at 0 but coming out. And that's usually the logic that people use, is that they say if the shape parameters or if a coefficient of variance of your gamma distribution is small enough, and a gamma and a log normal look actually quite surprisingly similar. And by that it means we use this, which means in terms of regression in inference, it's a standard technique whenever you want to make a maximum likelihood estimation or some model fitting, assuming what they call over-dispersed count data. You have to you might typically use a negative binomial likelihood for that. What helps us here is a bit that many of these fitting procedures, they are usually only sensitive to the first 2 moments of their distributions anyway. So only on the, if you replace a distribution by another one which has the same mean and variance but differs in kurtosis and skew, then this often doesn't really change the outcome of these things. So this is a decades-old standard shortcut to go over this negative binomial, even though usually you don't have any good justification of why you use the gamma in the first place. And in single cell sequencing or in general in transcriptomics, that's also what we always do. And using this, we now get here these values. I'm still, now I know why it didn't work. I have to add a 0.01 on both the saturated and the other model. Now we can see here how with 0.01, how big the gray one is. So what I can also do is, of course, here I had this histogram of deviance residuals. This was the deviance residuals for the Poisson. This is the deviance residuals for the negative binomial, which actually doesn't look that different if I now think about it. Maybe I made my size really too small. But something that people like to do in R is, if they have this deviance residual and want to know how much does it deviate from a normal distribution, there's this QQ plot. Who has seen QQ plots before and knows how to read them? Okay, for the others, you see I have this histogram, and I might wonder, is this a well approximated by a normal? What we expect about a normal is that 68% of the residual of the values are between -1 and 1, and 95 between -2 and 2, and 99.3 between -3 and 3. It's just the usual standard quantiles of the normal that we always use as a rule of thumb. And what we do now here with this QQ norm thing, what this does is it takes these, let's just show you how this works. I take my deviance residuals, these here, FRES, and I sort them. And let's see how many do I have here. Length. And now I compare them with what would I have gotten if I had used a normal distribution. So let's quickly get this here. And so I take a sequence of normals. So sequence from 0 to 1 with length 14429 plus 2. And when I remove the first and the last one, so from 2 to 4428. 4428. So what I now have is numbers from length. Have you done this now? Yes. So what this here is, if you look at it, it's just equally spaced. It's just equally spaced numbers from 0 to 1, equally spacing this thing in 1800 things. And now I put these into the Q norm function, which gives me the normal quantiles for this. So the corresponding Z values. Plot that now. And you can see now the cumulative normal function, the quantile function of the normal. So if I were to take 10,000 normally distributed values, then this might be a typical thing of it. I can also show you this here. I take 10,000 normal distributed values. R norm, 10,000. And instead of plotting them as a histogram, I sort them and plot them as I just had it here. You see, it looks like this. If I have less than them, it might look a little bit random, but if I have so many as I just had, we really get. So this is sort of a typical thing of normally distributed random variates in sorted. And I compare with sorted random variates, which I have here now. I compare them with my sorted deviance residuals. $dev res. And the trick is now to get this here right, that we get the right numbers. N-routable. How many are these? 14429, 14428. 29 plus 2. Here it has to be a 9 as well. And what I now Q norm, what I would get now, if I did it correct, is exactly this plot. So what this plot does internally, it calculates, it takes my 14,000 random values, sorts them, and plots this on the y-axis against the same number of random variates drawn from a standard normal. And then you can see here, if the data that I would get were actually normally distributed, then I would just get a diagonal line with slope 1. But as I can see here now, this here is on the diagonal line as slope 1, so you can see the negative residuals, they have nicely the shape of an actual normal. Here around 0, our normals seem to be a bit more flat, but the positive residuals, they go much farther out. Like we would expect, if we only have 10,000 values, we would expect that the Z value of a normal never goes above 4, but in fact we go all the way to 8. So this shows us that we have that our right tail is much fatter than a normal, while the left tail is as it is. So that's how a QQ plot is useful. It shows you, compares you the fatness of your tails with a normal distribution. And that's what I've used here in order to see what to see how far this stuff goes out. Okay, so that was, so far, we've discussed a bit about how to do diagnosis on our Poisson local regression fit in order to see how much of the variance we see is actually caused by Poisson noise and how much isn't. So to go back to the plot we had initially, that one here, the way how we can interpret is saying, if all the points were staying within the gray stuff, or maybe within -1 to 1, or perhaps going a little bit further out, then we would say, yes, this the the fit explains all the variance it can, and the remaining variance is only Poisson noise. But here we see clearly that there's a lot of biology going on, which is not captured by the pseudotime. So reducing our data to this one-dimensional pseudotime is not appropriate, because there is also information gained by making comparison within one pseudotime bin, saying that for one given pseudotime, we have cells which have much higher and cells which have much lower expression of these genes, and they might also differ in other aspects in a biologically meaningful way. So we don't really want to, if we want to smooth our data, if we want to smooth out the Poisson value, one primitive way would be, or not primitive, but one way that we've discussed so far is that we use this local regression to replace each value with its fitted value, but where we lose a lot of information. So let's try to do something which doesn't push us onto this one-dimensional line. And the simplest that we can do is nearest neighbor smoothing. We remember that for the UMAP and for the clustering, we always had this neighbor graph where we connected each cell with its 20 nearest neighbors. I have done this up here at the beginning, where I calculated here the 20 nearest neighbor for each cell according to its PCA coordinates. And we got this NN object, which had these two slots here in NN dollar index. It tells you what are the 20 nearest neighbors of cell 21 and how far are they away in Euclidean distance in the PCA space. And now let's use this to replace our, to do some very simple, smoothing. Namely, for every cell, we don't take the expression only of this cell, but we average over its 20 nearest neighbors. And let's first do this and then see how far it got us. So the way how I do this here is I pull out from the counts matrix the counts for our gene AQP4. I take the colsums to have my totals. So that's what I want before. And now I need to get the neighbors. And the easiest way I can do this, if I say NN dollar index, comma 2, for X, or comma 3, then this gives me for each cell its third nearest neighbor. And if I use this to index AQP4, to index my vector of counts, then what I now get is this new vector, which I should read as follows. This here is not the count of the first cell, but this is the count of the third nearest neighbor of the first cell, and this is the third nearest neighbor of the second cell. And so I can now run here and go through, apply through all the 20 nearest neighbors. And get now a matrix where here we see the count of the first, second, third, fourth, fifth, and so nearest neighbor of the cell. And if I add up the row sums, I get the sum over all the nearest neighbors. And that's what I've done here. You see here is my function that I've just, my sapply that I've just made, and here are the row sums, and here are the totals. And now I get these things here. These are the sum of the 20 nearest neighbors for the given gene, and here for all genes. I put back the gene names because I lose them in the process. And what I can now do is I take my table, and in this table, I now divide the counts over the 20 neighbors by the others. And now I get a new fraction, which is now averaged over all of them. And if we look at this, what we can now look here at our plot. Maybe let's first, before we do this plot, let's do one other plot where we say ggplot plus geom point as x gleich y, y gleich yn and sum. So here 1, you see on the x-axis, you see the original fraction, and on y-axis you see the smoothed fraction. And what we can see is that all those cells which originally had 0 counts, now after averaging over their 20 nearest neighbor, they get some reasonable count value, because maybe the cell itself doesn't have counts, but its neighbors has counts. And this is why the original y values here, they are monomodal, and the smoothed values are bimodal. I quickly show you this here by quickly writing this into a table. Ist $y. So this is our this is our expression of aquaporine 4, and you see here this difference between those with 0 expression. With some expression is really hard to see. But if I now go over with neighbor sums, then we see a clear bimodal distribution. There seems to be neighborhoods where this has an expression and neighborhoods where it doesn't have an expression. And that's what we've gained now in that way. So we made this bimodality much more crisp. And let's have a look at how this now looks in the UMAP plot. This is, no, let's first look at the UMAP plot here. This is how our expression was before, colored by aquaporine 4 expression, and this is now colored by the neighborhood smoothed aquaporine 4 expression. You see it becomes much smoother. We see here how it gradually goes down, and we got rid of this so-called salt and pepper effect, where we see this couple of cells with 1 count among cells with 0 counts, which make it really hard to judge, and now this is smoothed out. So you see this is a primitive, simple way, which is quite helpful. We can also use this now to redo our smoothing plot. So here is the same smooth curve as before, but the y-axis is now not the individual cells fraction, but the fraction over these 20 neighborhoods. And if you compare this with what we had before, when we only had the individual cells fraction, you see the cells could only follow the line up to here, and then you were into the noise. And now in the new thing, the values actually follow the curve all the way down here to the bottom. We see here that it goes up again here. That's what we've already suspected before, that there's something weird going on here. And here is also something weird going on. We are consistently below our line. So, yes. So the meta cell stuff is exactly, so there has been a couple of papers which suggest to replace your cells by meta cells by always taking 50 cells together and say this is one big cell. The catch is, in my opinion, it means that we have to draw boundaries. Say, this is one group of 50 cells, this is the next group of 50 cells, this is the third group of 50 cells, which somehow we lose cells in that way. And just smoothing out each cell by its expression, we keep all our cells and still do the same. We don't put in this arbitrary decision. So that's why I never understood what the point is of using these meta cells instead of just smoothing in that manner. Because it's effectively the same, it only does some strange extra stuff. Also, we'll see in a moment that there's better ways of doing it, because this was sort of our warm-up, and now we try to get a bit to better ways of doing this. Because what we've now done, we averaged over these 20 neighbors. The 20 neighbors might have different distances. Maybe we should have put a kernel over it, so that neighbors which are closer have higher weight than neighbors which are a bit further out. But we can also do a quite different direction. So where was I here? Nearest neighbor smoothing. Here we have UMAP before smoothing, after smoothing, and that's PCA smoothing. Because at the moment when we do this neighborhood smoothing, imagine the neighborhood we define in the PCA space. So we have our 20-dimensional PCA space, and imagine this here as I'm a cell here in my 20-dimensional space. This is one PCA dimension with the other PCA dimension with the third one. Now let's imagine I notice that the cells to my right have a higher expression than the cells to my left, and that hence expression seems to go down in that way. Now you remember when we talked about this local fitting, we also did this approach. We started off by first saying, let's simply smooth, let's simply average under the kernel. And then we later realized, if we have a situation like this here, where we are sitting at that place, and at that point, the expression is actually currently ramping down, and we have more cells up here, and here we have only a few cells, then our average will be too high. But if instead of just taking the average, we fit a line, we will correctly notice that the cell is going down. So we used this for the pseudotime, where this axis was the pseudotime, where we said we should look along these axes not only at the average of them, but we also should look at the slope at this point. And the same logic I can do with my average over my neighborhood. I stand here in my neighborhood and I say, it seems that in this direction it goes down, in that direction it goes down. So I want to use the information about the directions in which my neighbors are in the same way I do this here. So one possibility to do that would be that I say, okay, I do the same kind of regression as before, but my covariate is not just one pseudotime, but it's all 30 principal components. But while this is what we conceptually want to aim at, we don't have to do it. We can do something much easier. Because remember that because we can use the PCA directly to smoothing. Remember last 2 weeks ago when we talked about PCA, we said that the PCA can be understood as an attempt of reconstructing the data. We have our data, we transform it, we have our 18,000 dimensional data or our 1,500 highly variable genes. We transform it to our 20-dimensional PCA space by subtracting the mean and rotating it with this rotation matrix, which rotates and then cuts out everything. And then what we then tried is that we rotated backwards by taking the inverse of this rotation matrix and came back to our 1,500 dimensional space. And then we compared these two here by saying, what is the difference between y, the original value, and the effect of rotating backwards and rotating forwards again? I shouldn't call it t because times y. And you see this here is not the identity because I've called it a rotation matrix, but it's just the left couple of columns of my rotation matrix, the first 20 columns of a rotation matrix. So if I return in, project onto the 20 columns and rotate back, I lose information. So this here will not be 0. And I said what my PCA does is minimizes this mean squared error here. And of course, if it minimizes this mean squared error in a way that we get that what we lose is mainly Poisson noise and what we keep is biological signal. So we might actually say that this here, that this part, which I call y hat, is not an imperfect reconstruction of our data y, rather it's a more perfect reconstruction because we lost noise. So we might say this is a denoised version of that, and we can consider the whole thing of projecting into PCA space and rotating back to the original space. We can consider this as a denoising operation, which should get rid of a noise. So let's try that. And that's what I've done here. So what I do is I take my PCA matrix here, PCA $x. You remember this is exactly if you project y to r. This is what we call x. And this is what our PCA algorithm does. It gives us a rotation matrix and it gives us the rotated and projected y. So that's what I have here. The 20-dimensional rotated the matrix which for each a cell gives me a 20-dimensional vector. And now I rotate it back into the original space. And as you might remember, as a as a preparation for the PCA, we centralized our data by subtracting from each gene its mean. So we should add this mean back. And if we do this, then I get the reconstructed data, which now has hopefully mainly lost noise and not so much. So let's look again at first here our noisy data for aquaporine 4. And now let's look at the PCA smooth data, where we took all the data, rotated into the PCA space to get PCA $x. That's what we've already done at the beginning when we calculated the PCA. Rotate back in the feature space, and then take from this rotated back thing only the row that describes our gene aquaporine 4. So here I take my back rotated stuff and put it in here, and here's what we get. There. Here is oh no, no dim names. PCA smoothed. It has row names. PCA smoothed. They somehow got lost, and if I don't have row names, I can't. So I have to copy over the row names from counts. All names counts. HVG. Exactly, we have only done this for the highly variable genes. So now if I do this, I get now again a smoothed version. And this now differs from our neighborhood smoothing, where we did the smoothing via the PCA. And because the PCA is a linear transformation, what it has implicitly done is that what I've just described, I stand somewhere, I see in one PCA direction I'm higher, in the other I'm lower, so I fit a slope. What, however, the PCA cannot do is make the slope variable. The PCA is a linear operation. The rotation is a linear operation. So essentially, the slope that I have put here with my arms, this is an element of a rotation matrix. It's the element for the cell for this one gene in, if I look in the rotation matrix, I have an entry for every gene times every PC component. And if this is one PC component, I'm looking at the expression of one gene, then I assume that this slope is fixed. So what we may want to think about is how can we improve on this, that we get a, that we allow the PCA to do a non-linear operation. That will be topic of next week. We won't get as far today, but I can already hint a bit at this. What we've done here is something that the machine learning people like to call an autoencoder. So in an autoencoder, you have a high dimensional feature space. Let's call it big N. And you go from this into a small feature space Rk. And then you go back to a big feature space, and you have some function which does this here, and some function which undoes it. In the hope, and then you ask, you find functions f and g such that g of f of y, so this thing here, minus the original, given the original y, let's say minus the original y, and this again summed over all the instances, is minimal. That would be, this is what PCA does. But we can use this here, we can also say, or such that some general function which we call the loss of g of f of y hat given given y summed over all the things should be minimal. So we try function which minimize a loss. And I've just said the obvious choice for the loss is here just the sum of squared distances between the original data vector and the reconstructed data vector. So what might be alternative loss functions which I could put in instead of that? We've done this already today, that we said in the first we have used just a mean squared criterion, when we replaced this mean squared criterion by another criterion which worked better. Namely, or we did this when we did our kernel smoothing, you remember? We switched to a Poisson likelihood, and that reconstructing, judging how good the reconstruction is with a Poisson likelihood allows us to say so instead of using the mean squared error, we minimize the deviance. And the deviance will give us a big error if there is biological differences which we haven't called for, but if the error is just explained by Poisson noise, then the deviance will be small. So if we put here as the loss the deviance or the likelihood, this will allow us to say it's okay if you can't reconstruct the part which is most likely anyway only due to the Poisson noise, but everything beyond the Poisson noise you should reconstruct. And this is called a denoising autoencoder. We have a noise process. We assume that our vector y is actually, our measured vector y is actually not the real data, but it has been distorted by a noise process, in this case Poisson noise. And we hope by using a loss function which penalizes only deviation beyond what you expect due to this noise process, that we actually get rid of a noise and our reconstruction in a way is better than the original. That's called, as I said, a denoising autoencoder. And to do it, we have to find here a loss which characterizes via deviance or likelihood our noise process. So we would use simply the Poisson likelihood as a loss. And here we would have to use functions which go down here. And the crucial part about this construction here is that we force the thing to go through this small intermediate space. So here we have an information bottleneck. We force the thing to make a good reconstruction, even though effectively it gets several thousand numbers, but it's only allowed to keep 20 numbers in the middle and then go back to the 20,000. So we force the system to make a decision of choosing a function f, which keeps the irrelevant information and gets rid of the irrelevant information. And in this way, we choose it to sort of try to separate the Spreu from Weizen. So in this case, the signal from the noise. And if we now use this loss criterion, just mean squared error, and for f and g, we give a restriction that only linear functions are allowed, then the optimal solution to this task is the PCA. However, from this generalized way of putting it, we will now recognize that first we should be able to consider the PCA as an optimization problem, simply as a problem. Find the matrices F and G which minimize this thing, and we just do brute force optimization and we hopefully get the same. And then once we've done this, then we can simply replace the loss function with something more convenient for our purposes. Yeah.
For example, you have the nonlinear and the linear function. That means that it doesn't work.
I thought about this. Yes and no. We would expect if a decoder, in a way, the decoder has to undo the encoder. So the decoder might not be able to, so this might cause the encoder to be close to linear. But it could actually be that we get better to our optimum if this is not exactly nonlinear, because it shouldn't perfectly reverse it, because it should undo the noise. If we use the mean squared criterion and force G to be linear, then we can probably prove that the optimal F will also be linear. If, however, we use some Poisson likelihood, then it might be that you're right, that for a for a decoding G, we might get in nonlinear F. Interestingly enough, it's a question I wondered myself, and this is on my to-do list since ages to try this out. Exactly, yes. This was precisely what I've also seen somewhere, and I was wondering, does this make sense or not? And as you've already said, of course, what we will do next week is we will first try to use for F a matrix. And then if I manage to get it, we will replace F by a simple two-layer neuronal network in order to get something nonlinear. And then we will see that this actually gives us quite nice results.
How much would you actually work with the encoded data? Because I know that a lot of people are very critical of these, like if you change data sets.
Yeah, so we have this thing here, the latent data here. Now, so far, we've always worked in the latent space because we used our PCA and we calculated all our Euclidean distances in this space. And that, of course, sort of makes sense to do this. And as long as our two things are linear, it makes sort of sense to do this, to work in here. Furthermore, if we stick to this linear thing, because the decoder is, if it's linear, it's just a rotation. So distances here and here are the same. So this is maybe the whole logic that we say we want to calculate the distances here, but it's much faster to calculate the distance here because there's fewer dimensions, and we will get the same anyway because this is linear. If we have nonlinear functions, when we get distortions, and now the big question is, which of the two distances are more reliable of the biological things? And there's two arguments in two different directions. The one argument might be that you say, maybe it's true that we are better off in this R to the K, because imagine a cell changes its state only a little bit, and this change causes most of the genes to stay where they are, but one gene to really shoot up. Now, and if this is a nonlinear function, this function might be able to properly see this, that it has to make this one gene go up quadratical or to a cube. Now, when we then calculate a Euclidean distance here, even if you're out in only one dimension, that can really blow up your distance. And maybe that's not what you want. So it could be that this thing is more homoscedastic in terms of state spaces as this thing. But on the other hand, given that this is a function, if this is a nonlinear function, there's nothing which penalizes the thing if it introduces a lot of distortions here. If a function would replace one of the elements in here by its square, this would completely blow up our distances, but it would be no problem whatsoever for the neuronal network to get the square into the F and the square root into the G somehow. So in that sense, we have no expectation that this thing is actually well behaved. Now, there's a couple of suggestions how you can force this thing to be well behaved. The first thing is the variational autoencoder, which essentially is the following. We make a little extra step in here. We make the thing extra difficult for the network by saying the network gets its data, runs its encoder to get the latent representation. And usually we would take the latent representation and give it to a decoder. Now we are mean, and before we give a latent representation to the decoder, we add a bit of noise. If we add a bit of noise to the latent representation, and we force the thing to be able to deal with this, we enforce that a small change in the latent coordinate shouldn't cause a big change here. So we force the decoder somehow, or we force the network to choose a latent representation where small changes here cause only small changes here in some reasonable way. One could say that we enforce some kind of Lipschitz continuity in G, if you want to think about it, because we want to penalize. Yeah, I guess you could say you're penalizing high Lipschitz constants. And that might help a lot. So variational autoencoders were originally meant for this generative model, you know, these eigenfaces where you have these 10 sliders and you can push each slider and you always get a new realistic face. And where you want to know where a slight change in it, you know, each slider is a latent representation. You want to know where the small change or this causes the face to change slightly, so that when we have a feeling that there is a smooth relationship between the slider position and the face we see. But of course, this might be helpful here as well in order to help us ensure that distances in this latent space actually are somewhat reliable or meaningful or tame and don't have any wild things. So this is another idea which is new, which I heard Fred Humprecht present last week in the single cell meeting, and I'm still not sure on whether this helps anything or not. He suggested that instead to penalize the determinant of a Jacobian of G, arguing the variance of a determinant of a Jacobian of G, arguing that what we don't want is that in some area of a latent space, this thing blows up stuff strongly and somewhere else it blows it up only a little bit. And you know, this way, the Jacobian, so the matrix of derivatives of every component of here to that, this Jacobian can be interpreted of telling you how stuff scales, how much a small change here blows up here, and the determinant tells you how much this overall blow up is. And if you say you want to penalize variance of a gradient, you say that any kind of expansion which happens due to G in the volume in the state space should be consistent across the whole latent space.
Like I know what the Jacobian is, how that can be.
The general idea of a determinant of a Jacobian is, if I get it right, and Andreas will correct me, if not, imagine you have some function from, say, let's keep it the dimension the same, from a 2D space to a 2D space, and you have a little volume element, and this is mapped now to a new volume element, then the determinant of a Jacobian is actually the volume scaling. And that means if it blows up differences, the factor by which it blows up difference should always be the same. And Fred had this nice, this cute little demonstration where he sampled points on the land masses of the Earth as 3D coordinates. And when he pushed it through his Jacobian penalized autoencoder to go from the 3D to a 2D and back to 3D, and then he plotted the 2D thing, and you could get a really nice representation of the Earth with all the continents keeping their shapes and all their little angles. While if you use a normal encoder, it gets completely distorted. But all his demonstrations were doing these things, like going from 3 to 2 dimension. But here we go from 1500 to 20 dimension. I'm not sure whether you can still, whether it's still realistic to keep your Jacobian determinant consistent if you have such a big dimension jump.
There was one thing I didn't understand. So why does he want to control the Jacobian going from the middle to along the G? I mean, I would expect.
I mean, there's some symmetry. It probably doesn't matter whether you keep this Jacobian fixed or that one.
For the whole thing, because in this minimization problem, you also consider.
No, because what Fred wanted, he wanted to show that he gets a 2D landscape on R. If he fixes the Jacobian of the whole thing of F after G, then he would still allow the thing to make some wild a nonlinear change going here and undoing it again here. And you,
Yes, but without the noise. So the thing removes the noise.
well, his wasn't a denoising autoencoder. Usual mean squared criterion.
Okay, in my opinion, what one should do is do the denoising and control the metric or the Jacobian along both maps.
I guess if you control the Jacobian in one map, you keep it in the other. But I think you're conflating a dimension reducing autoencoder and a denoising autoencoding. My goal at the moment is to denoise my data. Fred's goal was not to denoise the data. He went in with exact 3D coordinates of his sampled landmasses and got them out. He wanted to find a faithful low-dimensional representation, which sort of gives a faithful map. He didn't care about any denoising because he didn't put any noise into his data.
Would you agree that in the denoising approach, the issue with the metric also occurs?
Yes. And then the question might be that you want to have, even then I would rather penalize on that side, because this is the side which gets rid of a noise. And maybe to get rid of a noise, it needs to be something drastic.
Yes, and that's why I would suggest to penalize the whole thing, like what you do in this.
Yes, but if you penalize the whole thing, you skip over this thing and allow them, you can have a tamely behaved f, g after f, while the intermediate thing is wild.
Yes, but in denoising you don't care about it.
Yes.
That's why it's unnecessary.
Okay, but in denoising, I don't care about the determinant either. Because if the whole thing does something wild, it doesn't have any chance to fulfill my loss criterion anyway.
Do you say there can't be anything wild in the
No, because the denoising criterion allows me to really, with Jacobian, Fred's geometric autoencoder is only about getting a good latent representation. If you just want to denoise, you don't care about it because you know that this has to be tamely behaved. Otherwise, you wouldn't fulfill your loss criterion, which after all wants you to stay close. So this is where we're heading. And what we do to this extent is, let's here skip a bit ahead. So here you now see the PCA autoencoder. And what I then did next is, and this we will show you, look at in detail next week, but I can show you already a result. We can now improve on our PCA in two means. The first thing is to replace this loss by a Poisson loss. And the second part is to allow for nonlinearities here. So let's first look at the intermediate step where we switch from a mean squared loss to a Poisson loss, but keep the matrices linear. And so, people like to, there was a paper by a guy called Charles Towns who called this a GLM PCA, because he combined the idea of generalized linear models that we discussed 2 weeks ago, where we said a GLM is a linear model where we replace the least square criterion by a general likelihood to get away from a normal noise model. And we combine this concept of switching to another thing with the PCA, hence he called it GLM PCA. And I implemented the GLM PCA very differently from how Towns did it, but the result works quite nicely. So this here was my normal PCA with a normal loss criterion, the mean squared error loss. And now here I show you the GLM PCA. The difference doesn't look that impressive. You see maybe a little more crispy, but it gets more interesting if I look at this plot here, where we can now, no, that wasn't it. Here, this plot where we can now see how the thing follows the curve. Let's look again first. I had at the PCA, here again the normal PCA. And if in the normal PCA, I look at compare with my fitted curve. I need this plot here, and why doesn't it give me that? Damn it, I just want to show you this one plot. This comes from not preparing this stuff beforehand. And now we have this thing that I so hate about R. No. Exactly. What we will now see is that the normal PCA, it makes a nice reconstruction, as you can see here, that we trained our PCA on the log transformed data. You remember we put in this k over s plus 1, which means the smallest value we ever see is 10 to the minus 4. And if we then go back we will, if we then go back, the PCA reconstruction will also be bounded by this. Now, what the hell is wrong here? Can anybody see why it doesn't like that? I mean, expression PCA smoothed is a normal matrix. Something is really wrong with this computer today. And I can't press stop. And it's 5 minutes to lunch, and I only wanted to show you these two plots, and it doesn't give them to me. No, I don't want to terminate R. I want to see my one plot. So what the plot will look like is, we have here our curves, and of course our reconstructed data will look like this, where the PCA can't get below 10 to the minus 4. It's this one, yes, exactly. Why does your computer do what my computer refuses to do? So everybody can see here on Philip's thing how the reconstructed PCA data nicely follows the curve until the curve drops below 10 to the minus 4. And then it doesn't do its job anymore because we trained the PCA to reconstruct our log normalized data, which can't get below 10 to the minus 4 because that's the value that we've already always added. If, however, we replace the loss function by a Poisson loss and calculate this Poisson loss not on the level of log normalized data, but on the level of actual counts, we can go below. That's the way that we already used to calculate our smooth curve, which we did with the GLM. And if we now want to use our smoothing not only along the pseudotime, but in all direction, we get the same thing. Do you have this plot as well? Does it show the next plot?
On the GLM PCA?
Yes.
I know because we have to read this text, which I don't have. We saved the GLM PCA.
Yeah. What the hell? Why doesn't this thing do this? Okay. So what we then will see is simply that that you've seen Philip's thing, and then it will follow it better down and goes all the way down till the bottom, showing you that this actually gives us an advantage. And then I did the third thing and also added the nonlinearity by replacing the function f. Before it was just a matrix multiplication. Afterwards, my nonlinear function space will be one matrix which goes from the 1500 highly variable genes to a 300 dimensional intermediate space, then a ReLU, and then a second matrix which goes from the 300 to the 20 dimensions. Now, what's a ReLU? You can imagine if I have these two matrices, it seems that I have a much higher function space because now I can parameterize with all the elements of two matrices instead of only one. But of course, this is not true because if I have these two matrices, I can always multiply them, and then I'm back by the linear function I had before. So I have to put something in between the two matrices, which stops me from being able to multiply them out and to cause a nonlinearity. And the funny thing is, the neural network people, after several decades of trial and error, they figured out that it's completely sufficient to do the most primitive of all thinkable nonlinearities, namely replace all negative values by 0. And that's what we try next week. And yes, I'll probably upload this thing, and then you see the remaining two plots, but they might be nicer anyway when we see them next week. And yep, and then we've all added even a bit of neural networks to our course.